depends if you're male or female. But it's about 50 to 60%. I think it's females have more water because they have more fat, and fat contains a lot of water. Females have more fat because they need it to support childbirth. Isn't that interesting? Okay. What chapter are we on? 3? Is there no sound effect?
Hands.
What movie?
Look at that.
Right.
Look at that. Hands.
It's another Finding Nemo line. Okay. We're talking about water. And the book, this chapter 3 basically starts with a review of chemistry. Because to understand the water, you have to understand water molecules. And to understand the water molecules, you have to have an understanding of basic chemistry. So I know you've had chemistry. We're not going to spend much time on this. This is a chart of the periodic table. What is this a chart? What's the periodic table show you? All the different elements. And I like to play this little element song. You ever heard the element song? It says every element. It's great. I'm trying to memorize it. I play it in every class.
Hydrogen and oxygen and nitrogen and rhenium and nickel, neodymium, neptunium, germanium and iron, americium, ruthenium, uranium, europium, zirconium, lutetium, vanadium, and lanthanum and osmium and astatine and radium and gold, protactinium and indium and gallium and iodine and thorium and thulium and thallium. There's yttrium and terbium, actinium, rubidium, and boron, gadolinium, niobium, iridium, and strontium and silicon and silver and samarium and bismuth, chromium, lithium, beryllium and barium. Phosphorus and francium and fluorine and terbium and manganese and mercury, molybdenum and magnesium, dysprosium and scandium and cerium and cesium and lead, praseodymium and platinum and plutonium, palladium, promethium, potassium, polonium and tantalum, technetium, titanium, tellurium and cadmium and calcium and chromium and curium. There's sulfur, californium and fermium, berkelium and also mendelevium, einsteinium, nobelium and argon, kryptonium, radium, and rhodium and chlorine, carbon, cobalt, copper, tungsten, tin and sodium. These are the only ones of which the news has come to Harvard. And there may be many others, but they haven't been discovered.
You know them all now? I'm getting better at that. I show it every few years. Eventually I'll know them. Okay, so anywho, all these elements are different. Why is hydrogen different than helium? What's the main difference between those two?
Electrons.
The number of protons and the number of electrons. The number that you see at the top, that's the number of protons that the atom has. So if it has 1 proton, we call it hydrogen. If it has 2 protons, we call it helium. If it has 3 protons, we call it lithium. The names we give it are according to the number of protons it has in the nucleus. Okay? So this is how the elements are named, by their number of protons. Now, they also have in their nucleus neutrons. And the neutrons, the number of neutrons help determine this number at the bottom. So lithium has 3 protons, but this number at the bottom is its average weight. It has an average weight of about 7. So most lithium atoms have 3 protons and 4 neutrons, which give it an average weight of 7. You see what I'm saying? Some lithiums only have 3 neutrons, which would give it a weight of 6. But most lithiums have 4 neutrons, which would give it a weight of 7. And when you average all those together, you get 6.941. Did y'all learn this stuff in chemistry? Chemistry's freaking awesome. So that's what they're telling you on this periodic table. And for an atom by itself will usually have the same number of electrons as it does protons, because protons have a positive charge and electrons have a negative charge. So they've got to kind of even out. To balance the charges, you have the same number of electrons as you do of protons. So hydrogen has 1 proton. Most hydrogen atoms would have how many electrons? You got to have the same number of protons as electrons. So hydrogen has 1 proton. How many electrons would it have? 1. Everyone should be shouting this at the same time. Let's try it again. If hydrogen has 1 proton, how many electrons does it have?
1.
Yeah, see? My class is excited. If magnesium has 12 protons, how many electrons would it have?
12.
Come on, y'all do it. 12, it's the same amount. Let's try it again. If gallium has 31 protons, how many electrons does it have?
31.
Yeah, see? Woo! Okay, so then we get into what we call electron levels. So hydrogen has how many electrons? 1. 1 electron. Do you remember the octet rule from chemistry? The octet rule states that atoms want to have a full outer level, and an outer electron level. And most atoms want to have 8 electrons in that outer level to have a full outer level. That makes the atom in its lowest energy state, if it's got a full outer energy level. So atoms are always striving to get this full outer level. Now for most levels, having 8 in the outer level gives you a full outer level. But for some atoms, having 2 in the outer level gives you a full outer level, because the first energy level holds 2 electrons. First energy level can hold 2 electrons. The second energy level can hold 8 electrons. And the third and everyone after that needs 8 in its outer level to be stable. Do y'all remember the octet rule? Give me a big thumbs up if you remember the octet rule. No octet rule over here? Did you take chemistry?
Yeah, right.
Oh, y'all did it. So hydrogen wants 2 at its outer level. There's another atom here, oxygen. Oxygen has a total of 8 electrons. How many would it have in the first level? 2 in the first. How many would it have in the second level? 6 in the second. And I'll draw them up here. 1, 2, 3, 4, and then 5, 6. And I'm going to erase the ones in the first level because we're only really concerned with the outer level here. So oxygen has 6 electrons in the outer level. How many does it want to be stable according to the octet rule? 8. So what oxygen's going to do is it's going to share one of its electrons with hydrogen. What oxygen and hydrogen do is they get kind of close together. The hydrogen atom and the oxygen atom get close together. Let me squeeze the hydrogen atom in here tightly. And the hydrogen will share its electron with the oxygen. And this electron will go around both nuclei. And so the oxygen can kind of claim that electron as one of its own. So now the oxygen and hydrogen, we say, are bonded together. Do you know what kind of bond that's called? Nope. It's a covalent bond. That's a covalent bond. It's not a hydrogen bond. And another hydrogen can come and do the same thing. It can covalently bond to oxygen. And so this is what the water molecule looks like. H2O, and there's kind of a bend to it. Now the oxygen is stable because it's got 8 electrons in its outer level. The hydrogen is stable because it's got 2 electrons in its outer level. Everybody's stable and happy. But there's a little difference here from a normal molecule. We call this a water molecule because it's a bunch of atoms joined together. The oxygen tends to hog the electrons. The oxygen tends to pull the shared electrons closer to itself. Oxygen is an electron hog. Trey, are you getting any of this?
Yep.
Pick your head up so I know that you're getting it. All the way up. There you go. Very nice. These electrons being hogged by the oxygen mean that the oxygen is going to take on a little partially negative charge. And that's the symbol for partial charge. It's kind of like a musical note. And you do that minus, that means oxygen is partially negatively charged because it's hogging the shared electrons. Electrons are negative. So the negative electrons are close to the oxygen. The hydrogens here, they don't have the electrons close to them, so they're partially positively charged. Partially positively charged. So now what we say is, this is a polar molecule. If a molecule is polar, it means it's partially charged. Did you know water was like that? Water was polar? How many of you studied that before? Raise your hand high if you studied that water was polar. This is repeated. And that makes the water molecule like a little magnet. And if you have a bunch of little magnets in one place and you throw them together, what do they usually do? They'll stick to one another in a little blob. Let me show you that. If I take water, I borrow this desk, and I pour it on the desk here, it sticks together. If water wasn't polar, it wouldn't do that. It would just spread apart. But it sticks together. Isn't that cool? Look. And it kind of flows together. Water has all these strange properties because it's a polar molecule. And so here we see, this is a... should I clean the water off the desk? They used to have Kleenexes in here.
Just touched it.
Huh?
Right. Just touched it.
It's upside down. Here we go. So we call these bonds that hold the oxygen, partially negative, is attracted to a hydrogen that's partially positive, and they're held together by a really weak bond here called a hydrogen bond. It's really weak. It doesn't hold them together that strong compared to like a covalent bond or an ionic bond. But it does hold them together some. And it makes it so hydrogen molecules stick together. Do you know the word for molecules sticking together? There's a word for that. Cohesion. Cohesive. They're cohesive. They'll also, a water molecule will stick to a surface. If I take some water and I pour it on my hand here, and I kind of throw it on the board, it kind of will stick to the surface. Y'all see that? Kind of. Try it again here. Throw some water on my hand and then throw it on the board. It kind of sticks to the surface there. It's stuck to the board, and it's not really. Some of it, the heavier particles are moving down, but some of it's just sticking there. We call that what? Adhesion. It's adhesive. So water's cohesive, water's adhesive, water's charged, water's polar, water has hydrogen bonds. Water takes a lot of energy to evaporate. Here you see a bunch of water, liquid water, and all these little dashes are hydrogen bonds, kind of holding the water together. Now, if sunlight shines on the water can evaporate. It's because the sunlight gives the water molecules a lot of energy, and the water molecules start vibrating like this real fast. The warmer the water gets, the more they vibrate. And imagine a bunch of little vibrating molecules bumping into each other. They collide many billions of times, many millions of times per second. And eventually, maybe a couple will collide and knock another one out from the surface of the water. And these molecules just very slowly will go shooting out, one by one, and we call that evaporation. And the warmer the temperature, the faster the evaporation happens. But when one of these molecules leaves the surface, it kind of takes energy away from the whole system, because that was a fast-moving particle that's now gone. And it removes energy from the system. And it kind of cools off the area that's leaving, because now it's in the air. And so if you ever pour water on your hand or something like that, and then you let it just kind of let it dry, let it evaporate, it'll feel cool. You know, you get out of a pool and you're all wet, and the water is evaporating from your skin, it cools you. This is a way that organisms. This is why organisms sweat. It keeps them cool. Here it shows water at the various phases. When water goes from ice to liquid to gas, the appearance of the molecules change. And you need to know this. 0 degrees Celsius is the temperature that water freezes, or the temperature that ice melts. Water freezing is just going this way in temperature. Ice melting is just going that way in temperature. But you can see the molecules as a liquid are kind of arranged haphazardly because they're moving around real fast. But when you get the temperature down, it gets cooler, the molecules slow down. And they take on this regular arrangement. It's kind of a hexagonal arrangement due to the hydrogen bonds between the molecules here. And do you notice that there's open space right there? Empty space? Ice will expand when it freezes. And it's about the water expanding when it freezes. It's about the only liquid that happens to. It's because of the hydrogen bonds. And so what happens, and this is very important to marine biology, in very cold latitudes like on the Arctic Circle or down in Antarctica, the air is so cold that it freezes the water. And the water freezes into ice. But because the ice has this regular arrangement, it's less dense when it freezes, and the ice floats on top. The entire Arctic Ocean, up the North Pole where Santa lives, it's covered by a sheet of ice, and there's an ocean underneath it. But the air is so cold up there that it freezes the water, and so there's a layer of ice. In some places it's 8 or 10 or 12 feet thick, and in other places it's thin. but there's a whole sheet of ice floating on top of the ocean. If there weren't hydrogen bonds, ice wouldn't float because it wouldn't take on this regular arrangement. And it takes a whole lot of energy to melt that ice. But gradually the ice is melting up there because of global warming. And if you've ever seen the movie An Inconvenient Truth, they talk about this. The ice covering the Arctic Ocean used to be so thick that the submarines that were going under it, we have a bunch of nuclear submarines traveling under it because the U.S. and Russia were at odds, you know, back in the Cold War. And so they charted where these submarines could surface through the ice. And they would have to break through, if the ice was more than like a foot thick, the submarines couldn't break through it to launch their nuclear weapons. So they kept very specific measurements of the thickness of the ice. And we know from those measurements that in the last 30, 40 years, the ice has been getting thinner and thinner. And in the summertime, it almost completely melts. So there's not much ice there. And every winter, it gets a little thicker because it's colder. But it's starting to melt. So we'll talk more about that later. And that's from human combustion and burning of all these fossil fuels. Here's another property of water. It's called surface tension. Think of a big body of water. The water under the surface is pulling the water on the surface downward. There's a downward pull on the surface. Because of that downward pull, the water molecules kind of get stretched and pulled, kind of like pulling the surface of a trampoline down. There's a tension there that we call surface tension. And this bug is taking advantage of that. It can walk on the water and push down on the surface. And you could even, if you ever tried this, you can even take a paper clip and balance it on the surface of the water. The surface is very tight. And that's an interesting thing for marine biology. Organisms can take advantage of that and walk on water. Here's a little video showing water walking. I show this to my biologist.
Water is made up of many millions of molecules which are attracted towards one another. At the surface, the molecules are attracted more into the bulk of the liquid than to the air above, and that creates a tension at the surface layer. It's elastic, almost like a trampoline or the surface of a balloon. It's as if the molecules are always being pulled inwards. That's why water drops are round. The overall effect is that the drops are surrounded by an elastic skin. Walking on water is a talent possessed by members of the insect group. One of the first may have been the springtail. Springtails live in damp places, so they already have a high degree of water repellence, and they don't fall through the surface if they spring onto a pond by mistake. But some species of springtail live their lives almost entirely on the water's surface. It's the aquatic springtails that have mastered the art of walking on water. For them, the elastic surface is almost as solid as a floor.
How cool is that? Walking on water, don't you wish you could do it? You're too heavy. This is a picture showing a layer of ice on the top. Think about it. If ice didn't expand when it froze, the ice layer would get denser when it froze, because molecules, when they slow down, they get denser, and it would sink to the bottom. And if the ice layer sank to the bottom, then the next layer of water would freeze and then sink, and the next layer of water would freeze and then sink, and you'd eventually have the whole all the water would be frozen solid. But that doesn't happen because water expands when it freezes and so floats. And this ice insulates the water below it from the cold air, and it never freezes. Here's an elephant cooling itself by blowing water on its skin, and then the water evaporates and cools the elephant. And the lady's riding it, you see. She wasn't expecting that. That's what you get for riding an elephant. Now, here's another cool thing about water, which leads us to the lab we're going to do tomorrow. Water is a great solvent. Have you ever heard that word before, solvent? Water dissolves substances. And if you put a sugar cube or something in the water, or a cube of salt, they're showing a cube of salt here. Salt is made up of sodium chloride. Did y'all know that? NaCl. Common salt that you eat, like you put on your food, is mostly NaCl. Sodium, which has a positive charge, it's an ion, and chlorine, which is a negatively charged ion. You should have learned about ions in chemistry. Ions have either too many electrons or not enough electrons, so they're charged atoms. And so sodium and chlorine are both charged atoms that stick to one another. And remember I said water is a polar molecule? And so it's charged. So if you put salt into water, the charged water molecules, they show them here in that up-close picture, they kind of gang up on the charged ions. And if it's a negative ion, the hydrogens, being positively charged, will stick to it and pull it away from the surface of the cube. And the negative oxygens will stick to the positive ions and pull it away from the cube. And so what happens is your cube of salt will dissolve in the water and almost disappear. Would there be a way to bring back the salt after it all dissolved? To bring it back to being a cube? We're going to do it in the lab tomorrow. Can you guess a way?
Evaporating the water.
Evaporating the water. If you raise the temperature of the water, the molecules will start moving real fast, and the water molecules are small enough where they'll fly out. The sodium and chlorine are too heavy. Sodium and chlorine are too heavy, and they won't fly off the surface. They'll stay in the beaker. So what you're going to do tomorrow is you're going to evaporate the water and figure out how much salt is in our ocean water. That's your job for tomorrow. I want you to come up with a procedure, you and your partner. I'm going to put you in partners. I want you to come up with a procedure where you can figure out how much salt is in the water. Okay? And so here's what we're going to do. I want you to figure this out in these units, grams per liter. Grams per liter. And I'm going to put you in pairs right now. Listen to your numbers, and I'm going to include Elizabeth, and if she's not here tomorrow, we'll fix it. You're 1, 2, 3, 4, 5, 6. You don't have to turn it off. Leave it on. 7, 8, 9. So listen to your partner. 6. Raise your hand. 6 and 4. 6 and 4 are together. 8 and 1. Raise your hands. 8 and 1. Stephanie's going to be 10. Elizabeth's going to be 10. 5 and 7 are a pair. 2 and 9 are a pair. Raise your hand. 2 and 9. 3 and 10. That's Elizabeth. You're with Elizabeth, okay, if she shows. If she doesn't show, we'll change it up. And what you're going to do is you're going to get with your partner, and you're going to figure out tomorrow, I got seawater in 2-liter bottles. You're going to figure out how many grams per liter there are in seawater. In each group, I want to get an answer. And then we'll compare answers, you see. And I know what the right answer is. So we'll see if y'all get close to the right answer. So what I want you to do, we got about 4 minutes here. I want you to get with your partner, and I want y'all to come up with a procedure on your own. Don't share it with anyone else, of how you're going to figure out how many grams of salt, how many grams per liter of salt there is in the ocean water. Now, I'm going to give you a little hint here. If you say, well, let's take a liter of water and evaporate a liter of water into the air, maybe we'll heat it up or something, evaporate it into the air, and find out how many grams of salt there is left. It'll take a long, long time to evaporate a whole liter of water. And you can go ahead and do it, but it might take you all day. So you might want to come up with a procedure that's different than that. So get with your partner for the next 3 minutes. I want you to write down in your little books a procedure of what you're going to do tomorrow, and then we're going to come in tomorrow and do it. Okay, you can turn that off.